Physics Mathematics. The discipline is studied by students of all medical Russian universities, not only Russian ones. It can be said that the study of man begins with the study of physics. We will start the lecture with a number of organizational issues. Well, first of all, I'll introduce myself. My name is Natalia Alexeyevna, last name is Ladnich, and I will be giving you part of a course of lectures on the physics of mathematics. I'm going to teach classes from someone. I am an associate professor of the Department of Medical Physics and Computer Science. The study of the discipline physics mathematics ends with your faculty receiving a GEP sachet. The study of the discipline continues for one semester. That is, in the summer, you will have finished studying this subject. Next, it is mandatory to record lectures in our case. We are talking, well, first of all about the lecture notes that you will do for yourself. In other words, in higher educational institutions, the lecture still remains the main form of educational classes. Attendance, well, as far as possible, we will mark your presence or absence. As for the subsequent work with the lecture material, I would like to note the following. Any new information disappears from my head absolutely within 2 or 3 days. Therefore, during these 2 or 3 days, it is desirable that the student can find time to work on this lecture. That is, even if you learn everything perfectly from the first time in 2 or 3 days, there may be several concepts left in your head, and some examples, figurative examples. Well-conditioned material can also disappear from the head. Therefore, study the lectures yourself. It is also possible on the same day, for example, in the evening, when a lecture is given, or it can be repeated for 2 or 3 days. Then, this material will be assimilated, and there will be no need to sit at night before the differentiated test. There will be much less problems with academic debts, with deductions, with repeated courses of study, and so on. And now, as for the subject of medical physics. It means that our head of the department, candidate of medical sciences, Associate Professor Yuri Nikolaevich S. Moryakov, speaks very well about the subject and about the study goals on YouTube. Our department, the Department of Medical Physics of Computer Science, has its own channel. Please find this channel and watch it yourself. Repost, subscription is welcome. The first lectures there are devoted to the question of why physics is studied at a medical university. Well, now we will briefly highlight these issues, and let's start with the subject of the physics course at a medical university. So, we begin to take notes on the subject of study. The subject of the physics course at a medical university is the human body, first of all, the environment, as well as medical and diagnostic equipment. In connection with the subject of study, the goals of studying the physics course by medical students are determined. Well, doctors in general. First of all, the study of the physical laws underlying the processes of vital activity. For example, processes such as blood circulation will be considered, and accordingly, the laws that regulate these processes. The second is the study of physical factors and the basics of their effect on the human body. For example, in the course of medical physics, we will consider factors such as electric magnetic fields, ultraviolet procrastination, and the basis of the action of these factors on the body. The third goal is to study the physical properties of biological tissues, organs, and systems. As for the study of properties, remember almost any diagnostic method, starting from temperature measurement and ending with tomography methods, is nothing but a means for studying properties. Tissues, organs, and even entire systems. And finally, the fourth, the study of the physical foundations of the device and the operation of medical equipment. Very briefly, concisely, but nevertheless, we touch upon this goal of studying physics in medical infusion in particular. Let's move on to the next question. The next question we have is the specifics of biomedical measurements. Well, before we move on to measurements in medicine, pay attention to the concept of the term study. By studying in this case, we will understand the establishment of certain measures, patterns, that is, the relationship between the quantitative characteristics of the phenomenon well, in other words, any study involves the establishment of patterns. Physics is a natural science, that's why it's not a description of a phenomenon or process, but the establishment of a connection between the characteristics of the phenomenon. Since the characteristics are mainly quantitative, then write to me please, do you see the presentation? And now, well, great. Start taking notes then with the definition of studies. So, in order to study something in medicine or biology, it is necessary to establish a pattern or a relationship between the corresponding indicators in this way. Measurements in medicine often involve just physical or physicochemical measurements. Moreover, the range of physical measurements in medicine is very wide. It's the same body temperature, its pressure, its pulse rate, blood flow rate, electrical resistance of tissue, electrical potential. Physicochemical measurements. This is perhaps the most typical: blood pH, sugar concentration, and others. The very concept of measurement implies comparison. Moreover, the comparison should take place with a homogeneous value taken as a standard. Well, for example, measuring length involves comparing with a measure of length, a ruler, a meter, and so on. Measuring body weight on a watch, on an old scale, involves comparing it with a certain number of weights. The next slide is the very specifics of biomedical measurements, which we will talk about in more detail now. The specificity of biomedical measurements primarily lies in the diversity of biological objects. In other words, there are no two exactly identical organisms in the living world. There are no two identical cells, viruses, and so on. And the values characterizing them, of course, will always differ. An example is the height of, say, a person, weight, body temperature, parameters that even in homogeneous groups of people, and even in the same person, can change over time, even within one day. Hence the variety. Second, most biomedical measurements are indirect. For example, blood pressure is actually measured by measuring the pressure in the cuff. Naturally, any indirect measurement loses accuracy, but, as you understand, the integrity of the body is not violated. And the electrical activity of the heart, for example, we evaluate by the type of Eck curve. Although, in fact, only the electrical potential is measured, and that is removed from the surface of the human body. And the third reason for this specificity, any value in medicine is simultaneously influenced by many external and internal factors. External environmental factors are atmospheric pressure, the presence or absence of magnetic fields, the temperature of the outside air, and so on. Internal factors are genetic factors. This may be, for example, the influence of the nervous system. For example, the very fact of going to the doctor serves as a reason for, say, an increase in blood pressure. The time and place of measuring blood pressure in this way will also affect and determine more precisely the variability of these measurements. The variability of measurements, or the specificity of biomedical measurements, which, well, first of all it turns out, is that quantitative measurements should be multiple or multiple. These are the measurements. Such measurements are amenable to study. Science, which is called probability theory. In the topic of today's lecture, we will consider such issues as the probability of a random event, that is, the basic concepts of probability theory, basic laws of probability theory, including theorems. And part of the lecture will be devoted to the characteristics of random variables. Before we turn to the questions of probability theory, I would like to note the following. Medicine as a science has been formed for a very long time, but unlike other branches of knowledge, this pre-scientific period in medicine lasted much longer than in other fields of science. There are still doubts about the benefits of some conventional treatment methods. Remember? Maybe from history. It was generally accepted to treat gunshot wounds by burning with a hot iron or pouring hot oil. Enemas were considered another popular method of treatment in medicine. Moreover, with different contents, these enemas were used to treat various diseases, and perhaps the most common method of healing among physicians of past eras was considered bloodletting. Bloodletting, well, maybe along with the use of pious. In other words, methods that are still used to some extent today, but compared to that craze, say, in the 17th century, are much, much worse. In medicine, as I have already said, this very pre-scientific period lasted until about the 19th century. That is, only at the beginning of the 19th century. So, this is before. It's premature. Let's focus on this slide for now. At the beginning of the 19th century, practitioners began to appear, and doctors began to ask questions about the effectiveness of the same bloodletting. And the pioneers of such new approaches to the use of certain means or methods of healing were Jules Gavard, it was he who applied the methods of quantitative assessment of medicine. It was he who believed that in order for preference to be given to some kind of intervention, it should not only lead to better results than the compared methods of treatment. Here, but the difference in efficiency must exceed a certain threshold value, which depends on the number of observations. In his opinion, if the difference was below this threshold value, then such a method or such a drug should be ignored and considered non-essential. In other words, this is where, when more precisely, the foundations of evidence-based medicine were laid, on which modern medicine is based. And at the beginning of the 19th century, new diagnostic methods appeared, such as, for example, a mercury thermometer. At the same time, percussion and auscultation are introduced into clinical practice approximately. In other words, the range of measurements, the range of quantitative assessments that doctors can apply is expanding. At the heart of evidence-based medicine, there are such tools as the probability of a random event. In other words, evidence-based medicine is based on mathematical statistics. The basis of mathematical statistics is probability theory. It means that probability theory as a science, as a separate branch of knowledge, separated from other knowledge in the middle of the 17th century, and the reason for the emergence of probability theory, or game theory, as it was called, was the interest of many players in predicting winnings in gambling games. To the elements of the theory of probability, the subject at the beginning of, say, probability theory are random events. A random event is called an event, the outcome of which cannot be proved during the test. It is impossible to predict. That is, in contrast to the ordinary concept of a random event, we are talking, as well as frequently occurring events, and about events of chances that are quite small to meet. In other words, the general concept of a random event is an event whose outcome is simply impossible to predict. At the same time, this test or experience is called a set of conditions, stored conditions, in which it is carried out, in which it is possible to observe this random event. Probability theory studies patterns that are inherent only in mass events. In other words, repeated phenomena are the subject of the study of probability theory. Here, here's the slide you need. So, for quantitative, or rather for comparing one random event with another, a concept is introduced that is called the probability of a random event. The probability of a random event is a value that is denoted by the letter P from A. That is, P is the probability and A is the event in question, which is being studied or investigated in an experiment. The probability of a random event is calculated by the ratio of the number of favorable events, event A, or the event of interest, to the total number of outcomes. Here's a look at the formula. The first one in the classical concept of the probability of a random event. N is the total number of events. I repeat, M is the number of events favorable to event A. As an example of a random event, we can cite a lot of examples that surround us in everyday life. This may be the birth of a child of a certain gender, a boy or a girl. And then, let's say, to find the probability of a boy's birth, we need to know the total number of births in the country for the year, and the number of boys born at the same time. The relationship of one to the other will both give us and show us the probability of such a random event, as the birth of a male baby. Probability, more precisely a random event, an example of a random event, is the loss of one of the extreme cubes of a hexagram. This is a typical example that is most often used in the course of studying probability theory. It should be borne in mind that I have already said that probability theory works with mass quantities, that is, to study quantities that are repeated many times, and therefore the formula for calculating the probability of a random event, which contains small values of both the total number of trials, and the number of favorable events, it is well far enough from the truth. Therefore, note that there is another concept of the probability of a random event, the so-called statistical concept of probability, which assumes that the formula becomes valid in cases when the total number of trials tends to infinity. In other words, the greater the denominator of the calculation formula, the probability formula of a random event, the more accurate the formula is. The concept of probability of a random event should not be confused with the concept of risk, that is, if in the definition of probability we are talking about the probability of occurrence of any event with high chances, with small chances. But we are not talking about only adverse consequences. Then the concept of risk includes exactly the occurrence of adverse events that involve some unwanted losses, damages, losses, and so on. There will be such a thing as professional risks in your professional activity. Almost like in any other profession. Financial risks, technogenic risks that accompany the entire development of this humanity. Therefore, it is possible to find on some products such a sticker that warns that the use of this product, for example, fireworks, is based on one's own fear and risk. The probability of a random event can take a value in the range from 0 to 1. In other words, there is no probability with a minus sign, there is no probability with a value exceeding 1, since the number of favorable events can never be greater than the total number of events. The extreme value of 0 is 1. These are so-called impossible events when the probability is 0, that is, when during the experiment, the event of interest to us did not appear even once. The second bound, the upper bound of the probability of 1, is the so-called reliable event. This is an event for which more precisely, during the test, all tests had to end with the appearance of an interesting, or so-called favorable event. One of the basic concepts of probability theory is the so-called incompatible events. An incompatible event, please note, is an event that simply cannot happen at the same time. That is, the measured value in one well, in the same person, in a particular, say, patient, and can show both the norm and some deviation from the norm at the same time. Next, events are called independent events if the fact of occurrence of one of them does not change the probability of occurrence of the other. In other words, an example of independent events in medicine are events, for example, that characterize to two different objects. That is, patient's blood group number 1, patient's blood group number 2. In other words, there are events that can be related in one way or another. Well, there is, and there are events that are completely independent. The next concept is the concept of a complete group of events, a concept that we will also encounter in the course of studying probability theory and statistics. A complete group of events is understood as several, and more precisely, a group consisting of several incompatible events. Moreover, these events should cover all possible outcomes observed during the tests. In other words, in a full group of events, the test will always show one of the events belonging to this group. An example of a complete group of events can be, well, conducted, let's say, during a set of events that accompany a measurement of any magnitude. That is, by measuring the pressure, it measures the temperature. We get a value that falls into the interval below the norm. The norm is higher. In other words, there can be nothing else. With the same blood type. Determination of the blood type for the first time in a patient who is not yet aware of it. We can say in advance that he will have one group of 4. Such obvious examples, but the consequence of this concept is that the sum is that you can use this pattern to find the probabilities of other, say, unknown events. The sum of the probabilities of all events included in the full group of events is equal to 1. The concept of a complete group of events is related to the concept of opposite events. An opposite event is an event that opposes itself to each other. An example of opposite events is, well, for example, passing. The result of passing the medical commission. That is, healthy, not healthy, fit, not fit, the condition of any device there is on, off in the same way as a daylight bulb. An example of opposite events is, in particular, the result of passing the test. The result is a set-off or a non-set-off. There are two theorems in probability theory. Addition theorem, probability multiplication theorem. That is, the probability can be added, it can be multiplied. When they can and should be added, when to multiply, is delimited by these theorems. So, when it is necessary to calculate the probability of occurrence of one event out of several, then the probabilities should be added up. In other words, the probability of occurrence of one event from a number of others is always a value exceeding a single probability value. That is, the result always grows because we take the sum of positive numbers. But in the case when it is necessary to calculate the probability of a joint or simultaneous occurrence of independent events, in this case, the probabilities should be multiplied. The addition theorem is written down. I will look at the addition conditions as follows. The probability of event A1 or event A2 and so on, up to and equal to the sum of these events. That is, the probability of the first event plus the probability of the second event and up to the n event. In the case when it is necessary to find the probability of occurrence of event A together with event A1, together with the occurrence of event 2 and with event A3 and so on a n, in this case, the probability is multiplied. Well, since probabilities are multiplied less than 1 most often, well, imagine zero integers. Let's say 5/10 multiplied by 0, as many as 5/10. As a result, we get a value that is less than the product of the numbers of smaller units. This is a smaller number. In other words, the probability of independent events appearing together is always lower than the probability of a single event appearing. I have already talked about the specifics of biomedical measurements. This is a variety of biological objects and the influence of many factors. So, to study, and this has already been said, quantitative characteristics are required. And quantitative. In most cases, medicine does not operate with the concept of a random event, but with the concept of a random variable. In other words, most of the parameters of an organism, a living organism, can somehow be reduced to quantitative measurements. A random variable is a value that takes one or another numerical value indefinite, that is, also unknown in advance, and depending on many random factors, well, or reasons that cannot be taken into account in advance. Random variables are usually divided into so-called discrete and continuous random variables. A discrete random variable is a quantity that takes strictly defined numerical values. A discrete random variable is usually expressed as integers, id est a natural series of numbers 0, 1, 2, 3, 4, although it can take a value with a smaller step, but it is still strictly defined. That is, the number of red blood cells there, the number of passengers in the trolleybus train, and so on. The number of students eventually in the classroom. Of course, in biomedical measurements, the most common value is the continuous value. This is a value that can take any value from a certain interval. For example, continuous random variables can be attributed, well, almost all the examples that have already been sounded. This is body temperature. This is body weight, height. This is atmospheric pressure. This is the majority of anthropometric data. These are continuous random variables. In other words, the same growth measured with one or another accuracy is a value that always falls within a certain range of values. And it changes, let's say, in the same person with age, even during the day, or in the population in a certain interval, that is, without a step. Well, and what can be taken by us as a step? Let's say, when measuring pressure. We don't say 115/3 of a millimeter there, so that we have a column. Well, such a conditional step is a unit of measurement, that is, the accuracy of which the device measures this value. But in fact, pressure, temperature, height, weight can be measured with any accuracy. There would be the necessary equipment. The next question we are considering is the distribution of a random variable. So, let's look at this slide and do a little pinch. The distribution of a discrete random variable looks like a tabular representation of a functional dependence. But the peculiarity of the distribution of a random variable is to find out the relationship between other parameters in place of a and x. Look at the tables. The values that a random variable can take are placed. That is x1, x2, x3, and so on. This is the value that the random variable takes. When we talk about the distribution of a random variable, it is assumed that all possible values must be represented in this distribution. In other words, it is nothing but a complete group of events. Well, in other words, all the measurements obtained in the experiment, they are placed in this distribution. The second line of the presented distribution represents the probability of occurrence of one or another random variable. That is, the corresponding value of x is 1 and n is 1. These are, so to speak, parameters that collectively take into account the chances of appearing in a given random variable, in a given distribution. And here in such a bundle are the values of a random variable, for example, the height of a person, and the corresponding probability of appearing, say, to a person with such a height. The next growth value is the corresponding probability that evaluates this value. The difference from the table, as I have already said, is that, first of all, certain numerical parameters appear, which are taken by the value of x and their corresponding probabilities. That is, not a y, but the probability of a random event. Well, before we move on to the following questions, or rather to the numerical characteristics of the distribution of a random variable, let's take a little pause. Break for 5 minutes. We continue the lecture. The distribution of a continuous random variable, in contrast to the distribution of a discrete random variable, it is impossible to specify a nearby distribution, because for a continuous random variable, the probability of each individual value will be an infinitely small value. That is, it will be close to zero. Therefore, for the distribution of a continuous random variable, the concept of probability density is introduced, or the density of the probability distribution is denoted by the letter f from x. And look, we are talking about the probability of hitting one or another value of a continuous random variable in the value interval. In other words, there is a probability that, let's say, the measured temperature value will fall into the normal range, and the norm is 36 and 0-37. That is, not a value, let's say, is a specific occurrence of a specific event of a specific random variable, and the hit of this value is a certain interval. So, we now turn to the numerical characteristics of the distribution of a random variable. There are three of these characteristics. The first of them is the so-called mathematical expectation. Mathematical expectation is denoted by the letter large M. The random variable calculations that are supported in this experiment or test are indicated in parentheses. Mathematical expectation is essentially an arithmetic mean, but for a large, sometimes huge number of values of a random variable. The mathematical expectation is calculated according to the formula presented on the slide. In other words, in order to calculate the average value for a random variable, it is necessary to know either all possible values and take into account the number of repetitions of these values, or it can be calculated using the products of the values of a random variable by the corresponding probability. Probability of magnitude. The second characteristic is called the variance of a random variable. Variance or scattering is the scatter of values of a random variable around a mathematical expectation. This value is denoted by the letter d large from x. And by definition is the mathematical expectation of the square of the deviation of a random variable from its mathematical expectation. It is not very easy to perceive by ear, but in practical classes you have either already calculated, or you will count the value for the variance of a number of random variables and figure out this formula here. That is, how the difference between the value of a random variable is taken into account. And, accordingly, the mathematical expectation of this random variable, as the probability of occurrence of a particular value of a random variable, is taken into account. And, accordingly, the probability of such a deviation. The third characteristic of the random variable distribution is the mean square deviation. It is also called the standard deviation, is indicated by the letter sigma from x. It is calculated quickly as a square root with variance. Well, there are other ways to find the mean square deviation. In the sense of finding the mean square deviation is nothing more than determining the interval in which the vast majority of values of a random variable are placed relative to or around the average measured in the same quantities, in the same units as the random variable. Let's move on to the next question. This is a normal distribution law, and it's a different presentation. So, we consider the question of the normal distribution law, and how much time we will have to touch on the concept of mathematical statistics. Before we define the normal distribution law, we have a general idea of what a law is. The law, in particular, the distribution of a random variable, is a correspondence or relationship between values, that is, between the x and the probabilities of occurrence of a particular value, as well as the functional dependence. The distribution law of a random variable can be set using a table. It can be set using a formula, that is, graphically it can be set analytically. That's as far as possible. Let's try to set this for the normal distribution law as well. In addition to the normal law of distribution of biomedical measurements, there is also, for example, such a law distribution as Boltzmann's law. We will also encounter Boltzmann's law, or the exponential law, in the course of physics, for example, when studying radioactive decay. Well, or when studying the dynamics of the growth of the number of bacteria, the number of infected, and so on. These are exponential patterns. The normal distribution law is a slightly different form of distribution of a random variable, which is one of the fundamental laws of nature. So, what is typical for a normal distribution or a Gauss distribution? It is also called Gauss' law. The first value of a continuous random variable should be weakly dependent on external factors. In other words, such a parameter, for example, as body weight, should practically not depend on the width, latitude, longitude at which we live, from atmospheric pressure, and so on. The second condition is that the values of a continuous random variable should practically not depend on each other. That is, the weight of one person is practically unrelated to the weight of another person. There are, of course, exceptions when it comes to relatives, well, maybe people living together and having the same habits, eating habits there, like, for example, students living in the same room, and the third main influence on the variability of a random variable belongs to internal factors, that is, internal reasons that cause changes. Genetic factors, of course, first of all. Now, if these three conditions are met, then we assume that we have the same normal distribution or Gaussian distribution in front of us. A normal distribution means that the most probable value in the distribution should be a value equal to the mathematical expectation. For example, in any dimension, let's say, of the same weight in some more or less homogeneous groups, the most probability, that is, the most frequently encountered value, should be such a value as the average weight. Second, most values of a random variable are close to mathematical expectation. In other words, for the vast majority of, say, participants in an experiment to determine weight, body weight values should be close to the average. That is, someone has more, someone has less, but still most of the values will be concentrated in the area of mathematical expectation, that is, in the area of the average. And finally, values that are far removed from mathematical expectation have a low probability density, that is, they rarely occur in the distribution of a random variable. This means that the further the value of a random variable is from the average, the less often such a random variable will occur in a given distribution. This is typical for a normal distribution. As examples, you can write down to yourself that the distribution of such quantities as human height, weight, foot size, vascular length, and, well, I repeat, the vast majority of parameters that can characterize the vital activity of the body are subject to the normal distribution. Mathematical normal laws, or Gauss law, represents the following dependence. The letter F from X denotes the probability density of a random event. That is, the very characteristic that refers to the characteristic of the distribution of a continuous random variable. Then we see familiar concepts in the formula. This is the mean square deviation. Here it is sigma. Well, I missed 2 pi. The letter E in this case means the base of the natural logarithm. It is not an electron charge at all. But, well, I'm sorry that it's not very clearly visible. In exponents and fractions, the numerator of the fraction of the exponent is written a x minus a under the letter a. This is the mathematical expectation itself. That is, in fact, it would be possible to write m in parentheses x, but it would be an additional pile of notation. Therefore, such a short designation of mathematical expectation is introduced. So, This difference between each value of a random variable and the mathematical expectation is squared. In the denominator of the calculation formula, 2 is multiplied by sigma squared. Sigma is again the mean square deviation of the normal distribution, that is, the characteristic of the scatter of values around the mathematical expectation. The formula is complex, of course, to use, but we will not use it directly. We will use the results of known patterns. Pay attention to the first picture. It presents, drawn in different colors, 4 graphs of normal law distribution. What is a blue graph? What is red? What is green? What is some kind of orange? These are all graphs of normal law distribution, as normal curves or Gauss curves say. What is characteristic of these curves is that they are symmetrical. That is, if we draw a straight line approximately in the middle with respect to the placement of these values, these graphs, then we will see the symmetry of the distribution of values relative to certain average values, relative to mathematical expectation. In other words, each graph has its own maximum, and there is its own decline of these branches of the graph, which determine the spread of values relative to the mathematical expectation. That is, the offset relative to the axis on the graph is determined by this location, by the value of mathematical expectation, and the shape of the graph, that is, flatter or more pointed, is determined by sigma, that is, the mean square deviation. The smaller the deviation, IDS the smaller the spread, the more pointed the graph looks, and vice versa. In other words, the flattest graph is the largest sigma. Here sigma is equal to 5 for the orange graph. For examples, it is given in theory, in statistics, usually an example firm I don't know, management, probably now you can call it that, namely, the distribution of shoe sizes for men. In order to determine how much we order in a batch, we need to order, let's say, the 42nd size, and how much is the 45th. In particular, the normal distribution law can help with this. To study this pattern, look, 1,500 men were selected. Each of them had their foot size measured, and this is the distribution that turned out. That is, the 40th size was detected in 43 people, the 41st size in 142 people, and so on. That is, the maximum of men had a shoe size of 43,557 people. Here it is a point on the graph. The size of the AB 42 and 44 had, well, 215, 243 people, respectively. That is, these 2 points on the graph. And so on. In other words, look, the further from the average, that is, the further from 43, the lower the values of the graph, that is, the less common the values are. Everything is according to the normal distribution law. Well, the graph that we got, of course, does not look like a normal distribution law yet. That is, it does not look like this smooth curve yet. A smooth curve can be obtained by increasing the number of participants in the experiment. let's say not 1,500 people, but 15,000 people. And then the nature of the curve will remain the same. Well, in theory, it should become closer to the normal distribution law. Because the size of the feet, and this is a value that obeys the normal law of distribution. I have already characterized the property of the normal curve, or the property of the Gauss curve. The density graph of the probability distribution has a symmetrical bell-shaped form. The line of symmetry passes through the mathematical expectation of a random variable. A change in the mathematical expectation with the sigma unchanged leads to an offset along the x-axis. That is, if, say, the average height increases in a group of children there, then the graph of the normal distribution law, relatively speaking, simply slides along the numerical axis towards large growth values. The shape of the graph itself may not change at the same time. That is, if it does not change, if some new factors that affect this value do not appear there. Well, there should have been a number 3 here. The shape of the graph changes, that is, it becomes an island or canopy even if the mean value is unchanged. The mathematical expectation value is unchanged with a change in sigma. That is, sigma decreases. Sigma decreases. The curve contracts relative to its center, that is, relative to mathematical expectation, and vice versa. The distribution is blurred. For example, the group becomes less homogeneous. There may be people in the group with different diseases who are not absolutely healthy. And now some parameter becomes blurred relative to the mathematical expectation. In other words, the spread of values increases relative to the average. Using the example of the distribution of such a parameter as human body temperature. Here, it is a conditional norm for the temperature distribution. That is, the average value is 36 and 5, and the interval covering all possible values is 3 sigma. The graph of the normal distribution law, that is, there is a maximum, there is symmetry with respect to this maximum, and the second graph of temperature measurement in various pathologies is shown next to it. The average value is a temperature of 38 degrees Celsius, but the interval that covers all possible values is already 2 degrees Celsius. Not 0.5, but 2 degrees Celsius. That is, the graph shifts along the x-axis in the direction of increasing values, and the graph blurs. That is, it becomes more flat relative to, let's say, normal. The properties of the normal distribution law include the first coincidence of the mathematical expectation of the median and the mode of distribution of a random variable. In other words, in a normal distribution, these 3 values should be reduced to 1 point. Should be reduced to a single value of a random variable. In other words, the mathematical expectation or mean, the median of the distribution, and the mode of distribution are approximately the same value of a random variable, well, keep in mind that the median distribution is called the midpoint, the geometric midpoint, between the minimum and maximum in the distribution. In other words, it is just the middle of the segment on which the random variable is distributed. The mode of distribution is a value equal to the value corresponding to the greatest frequency, or the greatest probability of occurrence, in a given distribution. In other words, the motor distribution is the most common value of a random variable. So, the arithmetic mean or mathematical expectation, and the middle of the distribution, and the most probable value in the normal distribution law coincide. This is the first property of the normal distribution law. The second property is called plus-minus rules, plus-minus 3 sigma. The rule is that knowing, or more precisely, making sure that the distribution is normal, we can get, so to speak, new knowledge. We can project this rule and say that in the case of a normal distribution of a random variable, an interval of plus or minus 1 sigma should cover 68% of all values of the normal distribution. The interval plus or minus 2 sigma should cover 95% of all values of a random variable. And finally, the 3 sigma interval should cover 99.7 of about 1% of the values of a random variable. There is always a small backlash for significant deviations from the average values of a random variable. If we give an example of height, then these are, for example, dwarfs. These are giants, for example, whose height in adults is about a meter, or there are more than 2 meters. That is, here is everything that falls outside of 99.7% of the dimensions. Here we can say everything about the distribution. Continuous random variables and the normal distribution law. The next question, which we will begin only in this lecture. These are the basic concepts or elements of mathematical statistics. So, just like probability theory, mathematical statistics arose, well, when there was a need for it. If gambling was the reason for the probability theory, then the reason for the appearance of mathematical statistics was the development of monetary relations. That is, the same mid-17th century appearance of the insurance business, or the birth, so to speak, of the insurance business in connection with transportation, in particular by sea. The same questions about demography, health issues, which also could not be solved by simply describing or listing items 1, 2, 3, 4, and so on. In other words, there is a need for new knowledge, for new ways of processing accumulated data. The very concept of statistics means a certain state position or order of phenomena. Well, nowadays mathematical statistics is a broader general view of the concept of statistics in general. In other words, modern statistics not only fix the state of affairs, it also allows you to perform some predictive functions. In other words, mathematical statistics is now a branch of mathematics that deals with methods of processing, methods of systematization, and use of statistical data for subsequent scientific and practical conclusions. The basic concepts of mathematical statistics include, first of all, the concept of a statistical aggregate. But a statistical aggregate is a collection of relatively homogeneous, but at the same time individually distinguishable units, united for joint study. A statistical aggregate can be a sample aggregate, a general aggregate. General statistical aggregate. This is a set that covers the available for at least a mental study or a thought experiment. The units needed in this study. And what is a sample population? More on that later. In other words, first, we will consider the concept of a sample method, and then, accordingly, we will get an idea of the sample population. It means that a separate unit included in the statistical aggregate is called variance. That is, a lot of options that are of interest in the study are, well, or are more precisely a general set. That is, if such a concept is studied, for example, in a study as the blood sugar content of young people of student age, they're from 18 to 30 years old, then the general aggregate in this case should serve as the whole aggregate, covering all students aged from 18 to 30 years. This is to study them all. It is very difficult to measure each of them. Nevertheless, look, in the methods of statistical methods, there is still a method of continuous research. In particular, you can write as an example. This is a method that is used in state population censuses. This is a method that assumes that not a single resident inhabiting the country will be missed, but still has some. Disadvantages. In other words, not all residents of the country, all residents of the country, will never be available for a survey conducted during the state census. But nevertheless, such an idea, a swing at a continuous study, is one of the methods of studying mass random variables in statistics. The method of continuous research is used, for example, in the study of rare diseases. Of course, the most commonly used statistical method is the sample method. Selective method. You can write it down. In addition, this is the main method of studying statistics, has a number of advantages. The sampling method itself allows judging the numerical characteristics of the entire population, which are often inaccessible for research, by the properties of the sample. In addition, the selective method saves time, saves money and labor costs in general. In addition, the selective method sometimes receives information in cases where a complete study is impossible. Here are biomedical measurements, medical measurements. These are measurements very often, in which continuous research is not possible. Therefore, the main method of medical statistics is a selective method. I think this is the last slide in today's lecture, because we will postpone everything else for the next lesson. In order for us to be able to judge the entire general population from the sample must meet a number of conditions. The sample should be representative, IDS representative. The first condition of the sample is its typicality. Typicity means that for research or in research, objects typical of our conditions should fall into the experiment. That is, if one or another, say, course of a particular disease is being investigated, the effect on the treatment of some, let's say a drug, then the objects selected in the sample should be people, well, preferably with exactly and only with this disease in question, which is used in the experiment. The second condition for the representativeness of the sample is its objectivity. Students themselves talk about the objectivity of the sample and give examples in practical classes. The only thing I can say now is that the objectivity of the sample is ensured by the random hit of objects from the general population to the sample population, but how and what ensures this randomness, I repeat, we will talk in practical classes. As I said at today's lecture, there was the last slide. Let's stop. The rest of the material will be considered in the next lecture. Goodbye. All the best to you.